Hi, are you interested in learning about RISC-V, the new open source free instruction set architecture that's available, or Microchip's PolarFire SoC FPGAs which incorporate RISC-V? Then stay tuned for this next video. Hi, welcome to the lab. I'm Tim McCarthy. In this video, I'm going to show you how you can get started with the Microchip PolarFire SoC Discovery Kit. The Discovery Kit is a low-cost board built around Microchip's PolarFire SoC FPGAs, which incorporate a 5 CPU cluster of 64-bit CPUs based on the RISC-V instruction set architecture, which is capable of running Linux and real-time applications, a robust set of peripherals, and a large L2 memory subsystem which can be configured for performance or deterministic operation. The Discovery Kit is a great platform for developers, hobbyists, or students who want to explore RISC-V or Microchip's FPGA technology. In the box, you'll find the Discovery Kit in an anti-static bag, a USB Type-C to USB Type-C cable, and a card with links to the Quick Start Guide and more information. On the top side of the board, we have the Microchip MPFS095 PolarFire SoC device, which has 95,000 logic elements. We have 1 GB of DDR4 memory, 2 user push buttons, gigabit Ethernet, 8 user LEDs, and 8 dip switches, a 40-pin Raspberry Pi header, and a microbus header connect to any of hundreds of microbus clipboards, a USB Type-C connector for providing 5-volt power for the board, connectivity to the UARTs in the PolarFire SoC device, and connectivity to the embedded Flash Pro programmer for FPGA programming and debug, as well as developing embedded applications. There's also a 2-screw terminal as an alternative for providing 5-volt power. On the backside of the board, we have a MIPI connector for machine learning and video applications, and a mini SD card slot for booting Linux. The Discovery Kit comes pre-programmed with a DSP FIR filter demo. Programming the board is not necessary if you've just taken it out of the box, but I'll review the programming steps for anybody that might have programmed their board after they received it. Prior to programming the board, we want to take the USB cable, plug it into the host PC, and plug the other end into the J12 connector on the board. LEDs will illuminate, indicating the board has power. You'll need to download the programming files using the link shown here. When you extract the zip file, you'll see 3 folders. GUI installer, which has the installation files for the DSP demo FIR filter GUI, programming job, which is the bitstream for the DSP FIR filter demo, and Tickle scripts, which contain scripts to recreate the entire Libro SoC project. I'm going to launch the programming software, entering FP Express in my PC to launch the Microchip FPGA programming software. Next, I'm going to click New to create a new project, and I'm going to browse to where I extracted my files. In this case, you see the programming job file. I'm going to select top.job and click Open. And then I'm going to navigate to a location for my project. I'll select the same folder and click Select Folder, and then click OK. You should see a programmer number appear in the Flash Pro Express GUI. If you don't, check the board jumper settings and then click Refresh, Rescan for Programmers. Click Run to program the device. After a few minutes, the GUI will indicate programming passed, and you can close the software by going to the project menu and selecting Exit. Click Yes in the dialog boxes that appear. Now I've programmed the device, and I'm ready to run the DSP FIR filter demo. The DSP FIR filter demo takes advantage of math blocks that are in the Microchip PolarFire SoC FPGA fabric. Math blocks are optimized blocks to implement DSP functions such as finite impulse response or FIR filters, infinite impulse response or IIR filters, and fast Fourier transforms. This is a block diagram of the design that's in the PolarFire SoC FPGA for the FIR filter demo. A GUI runs on the host PC where users will enter filter characteristics and also signal inputs that are sent to the board and via a UART connection and received by core UART, which is an IP block from Microchip. The data is stored in the FIR in buffer and the FIR out buffer, and the coefficients for the type of filter that was selected are stored in the coefficient buffer. Core FIR is an IP block from Microchip which is used to implement the FIR filter function, and core FFT is a block that's used to implement the fast Fourier transform to show the frequency spectrum of the filtered signal. After communicating with the UART to make sure that the GUI can communicate with the board, coefficients and data are sent to the board, which are stored in the coefficient buffer and the FIR in buffers. Also the FFT real and the FFT imaginary buffers. Core FIR does the filtering operation on the input data using the coefficients that came from the GUI and outputs the FIR filter outputs or the filtered data, which is stored in the FIR buffer and also sent to core FFT, which creates the fast Fourier transform on the data and stores the data in the real and the imaginary buffers. The data is then sent back to the GUI via the UART interface and core UART so that we can display the filtered waveform and the frequency spectrum of the filtered waveform. Before I can run the demo, I need to install the demo GUI. And you can get the demo GUI in the files using the link that we show here. When you extract the zip file, you'll have 3 folders, and the GUI installation files are in the GUI installer folder. Navigate to the volume folder and then select setup.exe, right-click, and select Run as Administrator. You may need to log in as administrator to install the software. The GUI installation will start. You can just click Next in the dialog boxes to install the software. Now that I've installed the FIR filter GUI, I can run the demo. Launch the GUI by searching for FIR and selecting FIR filter GUI. The FIR filter GUI has 4 tabs, 4 pages: the filter settings, the filter input, the filter output, and the coefficients. And I'll demonstrate these as we go through the demo. In the first section, we're going to select the filter type, and we're going to put in some input signals. The FIR filter demo can implement a low pass, a high pass, a band pass, or a band stop filter. And there's different filtering windows that are available. We're implementing a 127 tap FIR filter in this design. If I select low pass, I can select one of the various different filter windows, and I can also select the cutoff frequency. Here we're showing 20 megahertz. If I click Generate Filter, you can see the filter response. And if I choose different filter windows, I can see differing types of filter responses. Down below, I can select my input signals. And here we're selecting 2 input signals. Signal 1 is 5 megahertz, and signal 2 is 50 megahertz. So we're generating a composite signal that you can see here, which is essentially a 50 megahertz signal riding on a 5 megahertz signal. You can see it better if I zoom in. And down below, you can see the frequency spectrum, the 5 megahertz and the 50 megahertz signal. The next thing I'm going to do is communicate with the board and send the coefficients and the data to the board so we can run the filtering operation and the FFT. So I need to click the Connect button. When I click Connect, it will ask me to press switch 1 on the Discovery Kit and then click OK. And this is where we're doing the communication to make sure that we can talk to the board. So now that I've selected my filter and created my input signals and communicated with the board, the next thing to do is to click the Run button. And this is where I'm going to send the data to the board, run the filtering operation, and then do the FFT. And now it tells me that the operation is complete. So I click OK, and I'll go to the filter output page where I'll see the output frequency and the frequency spectrum. So because I did a low-pass filter with 5 megahertz and 50 megahertz, and the low-pass filter had a 20 megahertz cutoff, I see the 5 megahertz signal was passed, the 50 megahertz signal was attenuated, and I can see the 5 megahertz signal up here. Again, I can zoom in if I want to see it a little bit better. We can go back and we can try other types of filters. So let's try a high-pass filter. So I'll choose a high-pass filter. I'll leave the same 20 megahertz cutoff, and I'll try a little bit different window here. So let's try this Kaiser output. I'll generate the filter. I'll use the same two signals, 5 megahertz and 50 megahertz. I'll generate the waveform. Then I'm going to hit the run button. And now we would expect to see 50 megahertz because we had a high-pass filter, and that's indeed what we see. So we have 50 megahertz, the 5 megahertz was attenuated, and we have our 50 megahertz signal up here. And we can do the same thing with band stop or band pass filters as well. For more information on the microchip PolarFire SoC FPGAs, the Discovery Kit, or Microchip's RISC-V solutions, please see the links in the descriptions below. That's all for today. Thanks for watching, and we'll see you again in the lab.